In this video, we look at a square parallel plate capacitor of size 25 cm and separation of 1.5 mm maintained at a potential difference of 300 volts. We are required to calculate the capacitance of the system and the charge on its plates. And then again, suppose the separation is filled with mica dielectric of relative permittivity of 7, that is dielectric constant of 7. Calculate its new capacitance and charge. Now we're given the permittivity of free space, 8.854 times 10 raised to the minus 12 farad per meter. And in solving this problem, you would recall that as a strategy, first of all, we define the parameters, the data that we know from the question. Of course, we've defined that the length of the square parallel plate is given us 25 centimeter, which is 0.25 meters by dividing 25 by 100, so as to express it in meter, SI unit. Now the distance of separation between the two plates is 1.5 millimeter. You have to convert to meters by dividing this 1.5 by what? 1000. It's the same as multiplying 1.5 by 10 raised to the power minus 3 expressed in meters. Now the potential difference is given to us to be 300 volts. So, to get our capacitance under this condition, in the first case, of course, you know there is no dielectric medium mentioned in the first case of the question, and so it means we're going to take it as what? Vacuum. So we are looking for capacitance, we don't know. We are also to get a charge, in that case, we don't know. First of all, let's seek for the capacitance. You will recall that capacitance of a capacitor with permittivity of free space is giving us C equal to, that's going to be E naught times A divided by what? The distance of separation. That's permittivity of free space times the area divided by what? The distance of separation between the plates. Now the area will have to be calculated from taking into account that the plate is what? A square plate. Is that okay? And so for a square, we now want to talk about the area of the square. Very important. Because this problem, it could have been that the parallel plate is rectangular in nature, and so you will seek for the area of a rectangle, which is length times width. In that case, the width of the rectangle will be given, alright? Now, this question is based on what? Square. So the shape of the plate is square-like. So the area of the square, we're going to obtain it, and you know for a square, the area is length square. That is the square of any one of its sides. So it means that this formula is going to be written as this, then area of a square is length square divided by what? The distance of separation. Does that make sense? Take note that this length square represents what? The area of the plate. So we move on, we can now substitute that this is now equal to 8.85, alright? Think 8.854, then multiply by 10 raised to the power minus 12, then multiply by square of the length, which is the area, 0.25, going to square it, and then divide by the distance of separation, which is 1.5 times 10 raised to the power minus 3. We can now obtain our value by pressing these values in our calculator. Let's do that and see what we're going to get. That's going to be 8.854. We're going to multiply it by 0.25 times another 0.25, that is square of that value. Then I'm going to divide by 1.5. So from here, I'm getting 0.37 approximately times 10 raised to power. Now this 10 raised to minus 12 and then 10 raised to minus 3. We move this minus 3 up, it will change to plus. So minus 12 plus 3 is going to give us what? Minus 9. This can still be expressed as 3.7 times 10 raised to power. What did I do? I moved the point from here to this between 3 and 7. Because ordinarily we prefer that a non-zero number appears before a decimal point, okay? It's not like a rule, but just formal. So moving the point one time to the right means I'm going to subtract 1 from this minus 9, therefore making it what? Minus 10. So this is the capacitance in the first case of the question. We now want to get the what? The charge. Is that okay? We want to get a charge on the plates. So for the charge Q, alright, we're going to recall that Q is equal to, recall that Q is equal to CV. You know that capacitance of a capacitor is equal to charge divided by voltage. So if you cross multiply, you get a charge to be equal to capacitance times the voltage. So you can substitute, the capacitance is 3.7 times 10 raised to the minus 10 calculated already. So we're going to multiply by the voltage, and that the voltage that the plate is maintained at is 300 volts. Once again, we'll reach out for a calculator. Let's see what this is going to give to us. So we have 3.7 multiplied by 300. It's giving me 1,110 times 10 raised to the power minus 10. That's going to be in column. Okay, once again, I might wish to move my point from here, go 1, 2, and 3. Okay, so that this will still be 1.11 times 10 raised to the power. I move to the point 3 times to the left. So I'm going to add 3 to this minus 10, which will give me minus what? 7 coulomb. So this becomes the charge on the plate. We're going to take a break. When we return from the short break, we'll now focus on the second part of the question, when the space between the plate was filled with a dielectric material mica with dielectric constant of 7. And now, you're welcome from the short break. We want to look at the second part of the question. Suppose the separation is filled with mica dielectric of relative permittivity 7. Calculate its new capacitance and what? Charge. In the second part of this question, we don't have a dielectric material whose dielectric constant, that is relative permittivity, is what? 7. So we have to obtain the capacitance in that case, as well as the charge on the plate in that case. Alright? So it's pretty simple. Okay? It's just for us to replace the permittivity of free space with the permittivity of this dielectric material, which is mica. So we're going to recall that given a dielectric material, capacitance is given us the permittivity of that dielectric, right? Times area divided by what? The distance. But we know that this permittivity of the material is equal to, well, the relative permittivity, that is dielectric constant of the material, times permittivity of free space. So we replaced this permittivity of mica now, alright, with dielectric of mica times the permittivity of free space. And then multiply by area divided by what? The distance of separation. Now, I want us to look at this. You take note that this part of this equation is equal to the capacitance of the capacitor with vacuum as the dielectric, or air as the dielectric. Is that not so? And that's what we obtained already in the previous video. Alright, we got it as 3.7 times 10 raised to the power minus what? 10 farad. So we can rewrite this capacitance to be equal to Kr times C naught. Where this C naught represents capacitance of the capacitor with vacuum as a dielectric. Like I stated previously, we had that C naught is equal to 3.7 times 10 raised to the power minus 10 farad. So we can just simply substitute our Kr, that is dielectric constant, is 7 times 3.7 times 10 raised to the power minus 10. And of course, let's see what this is going to give to us. We shall multiply 7 by 3.7. So it's going to give us 25.9 times 10 raised to the power minus 10 farad. Okay, we can still write it as 2.59 times 10 raised to the power minus 9 farad. You know, I move the point once to the left. So this is going to be the capacitance of the capacitor with mica as dielectric. You notice that this capacitance, alright, is greater than the capacitance when vacuum was used. That's the previous case. So what does that tell us? That once you replace maybe the space between the parallel plate, if it is filled with a given dielectric material, it increases what? The capacitance of the capacitor. Of course, we encountered that already when we discussed the factors that affect capacitance of the capacitor. It was stated that the permittivity of that material affects the capacitance. In what way? The higher the permittivity of the material of the dielectric, the higher the capacitance. Of course, we are saying that in this case, right? Now, I want to calculate for the charge in this case. For charge, alright, we're going to recall that Q is equal to CV, so that our Q is now equal to capacitance with dielectric of mica That's going to be 2.59 times 10 raised to the minus 9. We shall multiply by 300, which is the given potential difference. And then, if we do this, let's see what we're going to get. 2.59 times 300 times 300. That is 7,770 times 10 raised to the minus 9 column, which is still equivalent to 7.77 times 10 raised to the power. You're going to add the 3 times and move to the point to this. That's going to be minus 6 column, right? Good. And that becomes the result. This result can still be quoted as 7.77 micro column because 10 raised to the power minus 6 is micro, right? So this is how we approach this problem on the board. It's a simple one.